The recording is on. Okay, hey guys, everybody, welcome. Can you confirm you can hear me and see my screen? Like people, students mainly. Maybe like unmute yourself or chat. Okay. Students, can you confirm you can hear me and see me? All right, yes. Okay, I got one yes, so that is by rule of induction should work. All right, so welcome. So today we are going to talk about the something called transformers and deep learning. So this is a slide from last semester, so ignore the date on it. So far in this class, you have learned the basics of natural language processing. So, oh, by the way, I cannot see the chat window, so unmute yourself if you have a question in between. So my name is Mithun. I'm a research scientist here. So today we're going to look at deep learning and transformers. And the reason we are doing that is everything these days is large language model. For example, ChatGPT is large language model. Any of the new ones like DeepSeek, etc., are all large language models. But deep inside, they all are something known as neural networks, and the next level of that is transformers. So they all use the same thing, neural networks internally, and something called transformers. So it only makes sense that evolution-wise, this is the next step in your learning, which is about deep learning and transformers. Okay, so I want to start this lecture with a question of identify these famous people. I'm gonna try to find, okay, got it. I found the chat window, so you can either like answer in the chat or unmute yourself. Okay, does anybody have an answer? Okay, Aditya says no one and Koi says no idea. Okay, so the answer is, Aditya, why did you say no one?
Because I couldn't recognize any. Yeah.
Okay, perfect. So that's true because these are not real people. These are all people that were generated by AI or currently a large language model. So the example I give here is these days large language models are capable of doing all this, including generating people that don't exist. Right. So welcome to machine learning. Now, there's a little clarification of the term machine learning and how it's like machine learning, deep learning, neural networks. You might have heard all that being used interchangeably, but historically, there's a slight difference. Machine learning is the term used for typically more statistics-based algorithms, while deep learning, transformers, large language models, they're all things that were used related to anything neural networks based, so which we will learn about soon. So welcome to deep learning. So I'm going to close my uh, chat window until I ask another question. So you might have heard of all this, like including ChatGPT, Llama, and all those things. So the question I want to ask you is like, how many of you have used ChatGPT? Okay, I see one reply. Yeah, okay. Yes, almost everybody has used ChatGPT. Oh, sorry, I think yeah. So almost everybody has used ChatGPT. Now, how many of you have used DeepSeek? Okay. So have you accessed it more as like a chat interface, or have you accessed it as a programming interface? Okay, so I guess you have not used DeepSeek, but that's okay. Um, Now, my question is, what is your definition of large language model? What do you mean by that? What do you think is a large language model? Just take a guess. We'll make this more interactive session. Okay. Hoikivo says it is trained on many data points and the answers can be generalized to answers not labeled before. Correct. And Aditya says ML model trained on large data set that can read, process, comprehend, and respond or generate text. Okay, perfect. Both your answers are correct. So large language models are these huge machine learning models which are trained on a lot of data. And yes, you're right. It uses one of the techniques it uses is tokenization. Now, let's look at deeply into how it works. Like I said, we'll start with deep learning and we'll start with transformers. So here's another question for you. Here, if I say I went to the bank to blank, can you fill in the blanks? Okay, Aditya says to draw money. Sounds good. Harry says to open an account. Okay. And any other answers? Okay. So instead, if I tell you I went to the bank to do some fishing, is that a wrong statement?
Yes.
Why?
Because you don't go to the bank to do fishing.
Fair. But what if I was going to a riverbank?
Ah,
See? I mean, if let's say I just said bank, right? And you live in like a place where there is more river banks than there is bank, a financial institution, right? And it's more, let's assume you colloquially you use the word bank and everybody around you understands it means a river bank. So the answer is exactly what Hoike said. It depends on the previous and the context afterwards. So everything these days in English at least especially is everything is dependent on the context in which that word is used. And this is known as word sense disambiguation. It's a very tricky problem in English, and a lot of older languages doesn't have that problem because English is a very new language. Its vocabulary gets reused, while the older languages most likely have a independent word for each of these things, or you can build it up. Now, the reason I'm saying all this is context is very important at this point, as you can see. Context, I need to explicitly say whether I went to the bank to withdraw some cash or I went to the river bank to catch some fish. So now, in short, I'm saying all this to prove the point that language is a hard task, at least English is. Now, here's a question like, how do you think humans learn a language? Let's say you're a baby who is growing up, 1 year old, 2 year old. Now, how do you learn language? I mean, don't worry about the answers there. I just want you to like think about yourself. Okay. Practice, fine. So let's say the first word you learn is mom, right? So do you really understand what that means in terms of a noun and object, a verb, and all those things? No, okay. Yeah, you don't, because in your mind, as a toddler, all you're hearing is, hey, this person here who I see a lot is called mom or ma, whatever, right? So you still don't understand. In your mind, it still is a mental model, what cognitive science people call it's a mental model. So let's say next you meet dad, right? So dad is, this person who shows up after mom or with mom. And then every time mom hugs me, she says, "Oh, baby, I love you." So you're subconsciously probably learning what love is. And the interesting part is humans have the ability to combine these mental models of words and meanings and build a new sentence from it, right? So the question is then, is that the right way to teach humans a language? Or not humans, machines the language? What do you think? Like if I give you a computer, infinitely powerful computer, let's say classical computer, which has 0 and 1, how will you start explaining what language is to a computer? Tokenize, okay. Tokenize what? So let's say you're a baby computer who was just born and you want to explain what mom is to the baby computer. How will you do it?
Maybe you need to fit it more sentences and show that it is this sentence refer to the mom, but other sentence does not refer to the mom, like a positive and negative sample.
Fair, okay. And another answer is, as computer understand only numbers, if we translate to some meaningful numbers, computer might understand. Fair. So both of you are kind of right. So the point I'm trying to make here is, like, you cannot start with initially, let's say, when you were talking about mom and you go back to the concept, the same idea of dad. Remember, like, bank having two different meanings. So we cannot start with that because we don't want to confuse the machine. However, humans have a different way of learning. We start with the meaning of a word and we build it from there. Whereas currently, what large language models do is to take a sentence, break it into small pieces, and then try to learn the meaning of bank from the words around it. So what I'm trying to come here to tell you guys here is currently how the way large language models learn is kind of a top-down approach where they take every sentence, break it down into tokens, and look for the word. The meaning of the word bank is dependent on the words around it, which you said is also known as context. However, humans, if you look at it, that is, I was saying, how do humans learn a language? We do a bottom-up approach where we start with the meaning of a word, then build a sentence, and then the combined words have a combined meaning. And eventually, maybe when you hear the bank example, you ask the same question. Oh, wait, I thought, let's say your dad says, "Hey, let's go to the bank to get some cash." So in you as a baby, in your mind, bank is a place where you go to get cash. A week later, your uncle says, "Oh, let's go to the bank to get some fish." And then you as a toddler is confused. So you ask the question, wait, I thought bank meant a place where you get money. But then somebody explains to you, oh no, wait, bank is also a place, a river bank can refer to a river bank, and we go to catch some fish. So as you can see, these are two opposing methodologies of learning. But currently we are using large language models, so which is a top-down approach. So let's talk more about that. So it's a hard task. The reason why this choice was made, like initially until 2013, natural language processing and scientists That's exactly what they tried. They tried teaching the machine, starting with meaning and then trying it to build it up using grammar or rules. Now, if you think about it, you as a child, you don't know anything called grammar. You just exactly follow what everybody else is saying. And eventually you realize, okay, when you put the words in this particular order, you elicit or you get a response, an intended response. For example, when a child is growing up and the child says, Mom, everybody starts clapping. And maybe child eventually says, Mom loves me. And then people are so excited, oh my God, the child spoke the first word or the first sentence. So there is this positive feedback mechanism. So that is how initially all this AI or the artificial intelligence models were trained. But it became a very hard task, as you can imagine, because when we were going bottom up, the sheer amounts of sentences you could make was getting very complex. Sure, let's say we started with mom as initialized as something, let's say a collection of zeros and ones, and love initialized as collection of another zeros and ones. And we combine them both, and let's say we add zeros or do some sort of an operation on it. But two words, it makes sense. But imagine like the infinite possibilities of word combinations, and not to mention the grammatical rules that have to go with it. So if you think about it, the current computers, they don't process the information in the same way as humans do. So eventually people had started asking the question, why are we trying to put the cart before the horse? If the machine doesn't understand bottom up, why don't we try top down? Which is, let's take the text that needs to be processed, which is I am hungry, and start the meaning from the meaning of the words around it, or in other words, context. So you see the big difference, right? So currently, the tokenization and all those things you learned are tricks that were created by scientists so that we teach the machine the way it likes to teach. Is it exactly the same as humans? Maybe not. But is it doing a good job as an AI, a copy of humans? Maybe it's helping us do a lot of things which was hard for us to do. Probably not an exact copy of human intelligence, but the jury's out on that, right? So we don't know that yet. So today we will talk more about the top-down approach because that's what you're here to learn. Currently, how does it work? And which is what I've been trying to tell you all this while is learn language from context. So you see, it's a very, very, very subtle difference. Like the meaning of mom is really not dependent on the definition of mom, but it's dependent on the words around it. The meaning of bank is dependent on the words around it. But I want you to think about this. Is the meaning of bank something that occurs with cash? Like I went to withdraw some cash, right? Or is bank standalone meaning? It's a tough question. I don't want you to answer because this is a big debating question that is happening right now. Nobody's complaining because things are working on from the large language model perspective. So people are okay with it, but some people have started asking the question, but wait, the meaning of bank doesn't really depend on the words around it. It also depends on the word around it. Coming back to tokenization, the way it works is, let's say that here is this big paragraph, which is somebody watched a movie and they are writing a review about the movie. It says, I love this movie. It's sweet, but with satirical humor. The dialogue is great, and the adventure scenes are fun, so on and so forth. For the very first thing, what the large language model does is it takes this big paragraph and breaks it down into small pieces, which you know are also called tokens. So that's where you get the word tokenized from. So you might be earlier wondering, why do we tokenize the words? And this is the reason. The immediate next step after tokenization is start counting. So it starts counting to find out how many times does the word it occur. Okay, so it occurs 6 times. So how many times does the word the occur? So the occurs 4 times. right? How many times does whimsical occur? Oh, whimsical occurs one time. So now it takes each of these words, like I said, tokenizes it into small, small pieces and starts counting. It looks at like review one, it says the word this occurs once. In review one, the word scary occurs once, right? And the good does not occur. While in review two, if you look at it, good does not occur, while in review three, good occurs. So you see where we are going with this, right? Now we are trying to tell the machine that, hey, it's a simple rule now we can come up with and say, tell me how many times does good occur? And the machine will say, oh, in the first two reviews, the good does not occur. The word good does not occur, while in the last one, the word good occurs. So then we try to tell the machine, maybe every time good occurs, it's a positive review, while every time it says scary, long, it's a negative review. So in this case, you can almost see that they are mutually exclusive, which is when the person uses the word long, he doesn't use the word good. So you see how we are breaking the problem of sentiment analysis, which is taking a whole word, big paragraph of movie review, understanding its sentiment, and trying to tell the machine what its sentiment is. Again, you might be thinking, but wait, that's not the definition of sentiment. Sentiment is something I feel after reading the whole thing. Sure, that's your human mind speaking. But remember, the machine is just zero and one, and this is the only way right now we can tell that to the machine, like things like this, like, hey, watch out for the word good, watch out for the word long. If the more number of times good occurs, you are supposed to reply back to me that sentiment is positive. The more number of times long occurs or scary occurs, you're supposed to reply back and tell me that the sentiment is negative. So machine is slowly learning all these rules. So that is the very first step of machine learning, which is rules. So after we have the rules like that, this is what earlier people were trying to do, which is compositional. Remember, I was saying before we went the top down approach, people were trying to get the grammar in there. Let's say here's a sentence, I prefer the morning flight through Denver. Then people said, okay, the scientist said, let's start giving it the subject and tell the machine, oh, by the way, I is a subject. It's called, technical term is end subject. So we started marking all this. And then we said, okay, what is my object? The object is I prefer flight. Okay, I prefer flight. What kind of flight do I like? Morning flight. So then that is called modifier in linguistics. And so this is what I said. This was the initial methodology that was tried. But soon people realized this is like a infinitely untractable problem because there can be so many combinations of subject, verb, objects as the size of the sentence grows. And not to mention the machines did not have that level of hardware to support it. So coming back to the first school of thought, so there are two major schools of thought, like I said, top down and bottom up. Top down is what the currently large language models use, which is known as learning from context. It's also known as vector space modeling. We'll get to that in a second. The bottom up is this one, which was originally, which we remember I said scientists were trying to model it like humans learn. Compositional. We are trying to compose a sentence and combine the meanings of the sentence and tell that to the machine. Now, coming back to the first school of thought, which is vector, which is the context-based school of thought, what people realized is that if you start counting the number of words and simply, let's say we put it in a vector like the one you're just looking at right now, we create a vector for the word good. So good is something like top down, the column good. The machine learns that good is something that does not occur in the first two reviews while it occurs in the third one. And it's also learning good is something that occurs with, let's say, in this case, I don't know. Let's do it other way around. Long is something that almost occurs with scary, which means a sentiment is sad or negative. So what happened was when scientists start plotting this onto a graph, they noticed a very interesting phenomenon. They realized that if you take like, after making the machine go through thousands and thousands of movie reviews or thousands and thousands of sentences, the machine said, okay, hey, here's a vector for queen, here's a vector for king, here's a vector for woman, here's a vector for man. So somebody was very curious. They tried plotting this on a two-dimensional Descartesian graph. And what they realized is if you take the vector of woman and you add to it the vector of king, reduce the length of the vector of man, you will exactly land at the point where queen is. I'll say that again. You initially start with the vector, or let's say you're standing here at the tip of the word woman, wherever the vector points. Now you reduce the vector of man from it, and then you add king to it. Then people realize, oh my God, that's the same vector as queen. Now that is what we call quantitative analysis. Now qualitatively, think about this. What is the definition of queen? Is queen a woman? Yes. Is queen a man? No. So we subtract the man. But then what is the other relationship? The other relationship is queen is a woman who occurs with king. So you see how people started going from a simple vector-based length-based thing into what we call the meaning space or semantic space. So remember, in the initial tasks, all they were doing was, hey, just watch out for good. If good occurs, tell me it's positive. If good doesn't occur, tell me it's negative. And the machine was just because it tried giving you exactly the same thing. Then people started noticing, oh, wait, maybe there is a method to this madness, which is maybe it actually makes sense that, oh, wow, okay, queen is a woman, but it's a woman who hangs out with king. So slowly people started realizing that there's a bridge between the vector and the meaning of the vector, like the way humans know it at least. And remember, individually, the vector doesn't mean anything at all, but everything is relative. So if I give a vector of queen and it is like, let's say like this, like 0, 1, 1, 1, 0, it doesn't mean anything to the human. But relatively, people started realizing that, oh, wow, it started when you compare one with the other, it starts aligning with the way humans know things. Okay, so I'm gonna keep talking because I'm sorry, I just didn't have a look chance at the window, the chat window. Okay, no questions. Cool. Any questions so far? Just feel free to ask. So these are important basics you need to understand before you jump in and start learning large language models or transformers. Uh, or rather, if you understand why they were created, it's much more easier to build what you're trying to build. It's like the deep knowledge that what do you mean by language? Now, once this kind of setup was done, people started using it for, let's say, real life tasks. For example, one of the real life tasks we saw already is sentiment analysis. So then they realized, okay, it doesn't just have to be movie reviews. It can be, let's say, an Amazon review. So, if the Amazon reviews had said the product is okay, I guess, people started moving from the two-class scenario, which is initially, remember, the sentiment was only positive and negative. Then people started realizing, okay, why do we have only two classes? Let's give it three classes. Can the machine understand three classes? Say if the sentence is my experience so far has been fantastic, our initial model would do fine, which is, let's say the initial model was we simply had one rule, which is, hey, every time you see the word fantastic, tell me positive. But then we walk into the world of ambiguity or neutrality, which is somebody says the product is okay, I guess. Now, how can we create a rule for that? What does okay mean? Like as humans, we understand it means like it's like a medium kind of lukewarm response, what we call neutral. But how do you explain this to the machine, right? So these were the interesting thought process that went through this historically in the minds of scientists. Like, hey, it's so obvious in our head, but how do I explain what neutral means? So they were easily able to explain what positive means, which is like a smooth trick. Like I said, fantastic, tell me it's positive. Useless, tell me it's negative. Everything was great until we walk into these kind of gray areas. So, so that is one of the tasks that these days machines are able to do, which is differentiate between these gray areas and tell you exactly what exact sentiment of the machine is, of the review is. Same as text classification. This is another task which we use. Now, if you start with ChatGPT, it can do all of it, right? All of these individual tasks. But you must remember 20 years ago, all these were separate tasks people were trying to tackle independently. So which is another definition of large language model. The large not only comes from the size of neurons used, but it comes from the fact that it can do multiple tasks together, including, say, for example, on ChatGPT, you can give it a movie review. It'll give you a sentiment. You can give it two emails, one spam and one not spam. It'll correctly classify it. So that is the major difference, that this is large and it is able to do multiple tasks. So now people do like not just, so the inbox and sentiment analysis, like 20 years ago, those were the very first tasks we were using the machines for. Now what do we do? Now we have the generative concept, which is the machine is able to reply back to you, putting the very next word, one word after the other. So there is the generative piece, which you must remember, generative was yet another task. Like text classification, we were trying to ask the machine, can you tell me, if I tell you sun rises in the blank, can you tell me what word occurs next? So that was a separate task in itself. And now combined together, it is not only able to answer your question when you ask, hey, what is the sentiment of this movie review? Instead of just saying positive, ChatGPT says, the sentiment of this movie review is positive. So it's combining multiple tasks, that it's classifying, it's also generating text, and it's answering you just like a human does. But you must remember, at the end of the day, these are all collection of rules, all working together. It's not really human. It doesn't understand exactly like the way it does, the way humans do, even though kind of it makes you feel like that way. Another task is machine translation, which is given two different languages. How can you translate from one from another? Again, ChatGPT does that all together. So how do these things work? So today's class is more like an introduction to deep, very, very deep inside. We already saw how part of how it works, which is they take the whole movie review, break it down into words or tokens, start counting which word occurs with which, and at the end of the day, it's a frequency memorization mechanism. So sure, if it's a frequency mechanism, why do we need neural networks, right? So let's quickly talk about what neural networks is. The neural networks was based on original neural network, which is the neurons in our brain. But neural networks are simply nothing but a reproduction of the neurons in our brain. Now, here's a very simple example of how I like to explain what goes inside a neural network. Trivia question for you again. Where do you see this sign almost on a daily basis? Or where have you seen this sign before? You can use the chat window or unmute yourself. Look at the chat window coming in 3, 2, 1. Speedometer. Yeah, perfect. Car speedometer. You're right. So this is what a little sign you will see right next to the cruise control if you have been in a car here in the US, right? Um, speedometer or the cruise control mechanism. The question then is, how does cruise control work? Let me start with this. What does a cruise control do? if you have ever used it or encountered it.
To maintain the speed.
Maintain the speed. Okay. So now that you made the mistake of unmuting yourself and answering, I'll ask a follow-up question. How does it maintain the speed?
I
Anybody can.
It
Okay.
first have to detect the current speed, and then if it is out of the range, then they will adjust, accelerate or decelerate.
Perfect. So what Hui is saying is that currently, like let's say you're going at 45 miles per hour, and you as a user have set the cruise control speed to 40. So what it is doing is what we call a control system or a closed loop. It's nothing but it's constantly checking the current speed, and it is comparing that with the expected speed, and then it is making a decision. The decision is, do I want to add more speed or reduce more speed? So in short, it's a constant feedback mechanism between the current speed and the expected speed. Neural network is kind of exactly the same. That's how it learns. So neural networks, like I said, if you actually open up the code for neural network, you will just see that it is two if conditions. If condition is based on the input that's coming to me, I decide what I want to do to it. For example, if my current speed is more than the expected speed, I send out the command decelerate or reduce the speed. If not, I send the command accelerate or I send the command stay. So you see how this is matching up with the same sentiment analysis of positive, negative, or neutral, right? So that's when scientists thought, oh my God, it's exactly the same thing. Like we have been using it all over the place. And that's how your brain works. The only thing is instead of one neuron, it probably is trillions or quadrillions of neurons all working together. And the scientists started asking the question, what if we started creating a huge combined beast or a network of neurons? And instead of using one neuron, which is if, else, if, else, if, else, can we use a collection of neurons to learn one task? So that is all neuron does. So if you look at it, it is a collection of individual neurons, a neural network. There's an input, there's an output. And the ones inside are called hidden layers. So it's a funny word. It just means like there are infinite amount of neurons in between. How much exactly it is and why it is that number. Its simple answer is trial and error. People have been mixing and matching neurons and suddenly they realized, oh my God, this architecture works. So in a way, it's a sad state of affairs if you look at it scientifically, because nobody knows why that architecture works, except they know it works. But coming back to the how neurons work, neural network works, is let's say in the input layer, I give a input which is my movie review, and we give this big paragraph of movie review to a black box. You can even call this a black box, or the neural network is a black box. Let's say it could even have been a human sitting inside the black box. But what happens is we ask the machine, here's a movie review. What do you think is the sentiment for this? And initially, the machine has no idea. It just randomly takes a guess. Like it first asks you, like, how many classes are there? So then we tell it two classes. 0 and 1, where 0 stands for positive and 1 stands for negative. So the very first time when you ask that question, all the machine does is it just picks one of these choices randomly. It says, how about the given movie review is positive? And then we as humans, we tell it, oh no, by the movie review I gave is negative. Now, what it does is it's exactly like your cruise control. It starts understanding what do we humans mean by negative? Or in other words, what is the difference between my current speed and the expected speed? You see how it's all connecting up, right? So the machine is starting to ask the question, or we write code to make it ask the question, which is, if you are at 45, what will it take for me to get to 40 if that was the expected speed? So it starts back propagating that difference. Or in other words, what is the difference between positive and negative? We as humans know that. But what we are making the machine ask is, what is the relationship between all these signals that's coming out of all these millions and billions of neurons and the word positive? Or in other words, when the human told me my answer was wrong, that my answer of positive was wrong, I, as a neural network, I look back at each of the signal that was coming out of each of these neurons. And remember, it's not just 0 and 1. When you divide it by 10 power 9, it's 0.001, 0.002. It's not binary anymore, the amount of signal that's coming out. So each of these neuron had like little contribution to the big neural network. And now we are forcing the machine to ask the question, what does this combination mean given the fact that this movie review is positive? Or given the fact that I said positive and the movie review is negative, or my answer was different than what the human expected. So machine looks back and like, I this first neuron in the first layer said zero point 0.2, but maybe I should have said minus zero point 0.2 or zero point 0.1. Now, second time we give it another movie review, and now it starts guessing. It starts saying, okay, let me start turning the knobs of each of, it's like a pipe, okay, the water flowing out of each of these pipes. Initially, what the neural network does is it's literally turning knobs of all these pipes until it slowly starts matching your current output with the expected output. It keeps turning, and slowly it realizes, if I have these pipes and valves and water flow in this particular combination, might be zero point 0.1 on the first tap, zero point 0.3 on the second faucet, zero point 0.5 on the second layer, fifth faucet. Nobody knows. So machine is literally playing a permutation and combination game, and it finally comes out with a combination of weights, or what you would have heard the term parameters, is nothing but how much should I open the tap number 2 in the second layer, how much should I open the tap number 3 in the fifth layer, etc., so that I, as a neural network, can match the expectation coming from human. Does that make sense? That it's exactly the same as backpropagation in a cruise control? Now, large language model is nothing, but instead of one or two movie reviews, we give it everything in the internet, and we sometimes give it labels like positive, negative. Sometimes we just say, go figure it out yourself. What are these kind of classes in between? And that's how what we have something known as large language model. So I'll stop here. You already have the basics of how large language models work. And the reason I'm stopping the theory here is I wanted to introduce you to some hands-on, which we already have. To get to the hands-on, so I'll upload these slides after this particular slide. We'll get into details of transformers and things like that. So transformer is nothing but a more complicated neural network. It's just like this, right? You don't have to worry about, instead of like one single input output, there is like thousands of input outputs. And transformers is used by every single large language model now. But I would rather, like that, those are the only next few slides. Here's the transformer history, and eventually everything in today has transformers, including ChatGPT. Now, I want us to try, at least before we end the class, I just wanted to introduce you to some hands-on or some programming by which you can start playing with everything you have learned so far. So if you go to UA-Data Lab, maybe Meg, you can post the link to it and click on repositories. This is the way I like to go. Look for this class, which is NLP-speech. And if you look at the chapter Introduction to Transformers, there's an IPython notebook or a Jupyter notebook called training_transformers. My stupid browser doesn't open it. So what I do is I usually download it and open it in Colab. So let me see if you open it, maybe yeah, there you go. You might be even seeing a link called Open in Colab. Click on that and let me try posting this in the chat. All right, so I think UA Data Lab already did that. All right, so once you get to this page of the Jupyter notebook, click on Open in Colab. And Colab is an online place where you can execute a lot of Python code. We have less than 12 minutes left, so I'll quickly run through this. So like I said, everything is transformers, but these days you don't have to worry about any of these things, how it runs internally, because the first line is pip install transformers. If you are familiar with Python, you know that this is how you install an executable or a collection of commands which people have nicely packaged for you. So we run pip install transformers. So every single new big large language model deep inside has transformers in it. The next thing you do is, I'm just going to clear the output so that it looks more cleaner. Right click, clear output. So the next line is from transformers import pipeline. So pipeline is something provided by, I need to introduce you to something known as Hugging Face. If you haven't heard of Hugging Face, you should go really search Google for Hugging Face. This is the one single biggest repository in the world of all the large language models. It was started in 2016, but it has become so big that it has close to how many models? Let's see. 50,000 organizations are using it. I'm going to say close to 1,000 models. Any large language model, you can find it here in Hugging Face. And in fact, Transformers is a model provided by Hugging Face itself, which is the fundamental, like I said, it's a model on which all the other models are based out of. So today I'm teaching you the fundamentals, and I'll show you how we can get to calling a GPT from command line too. So once you install transformers, you call it this way, which is from transformers import pipeline. And pipeline is nothing but a chain of commands, right? So just don't worry about it for now. This pipeline, if we can use it as a parent or an umbrella term for multiple subtasks transformers can perform. So remember, transformers, when they were created, there were separate transformers for each of the separate tasks. So individually, they were not large language models. So individually, people were creating these models and saying, hey, here, I want you to do sentiment analysis for me. And I give it two sentences. The first sentence is, I have been waiting for a Hugging Face course my whole life. It's pretty similar to our sentiment analysis task, which we saw in movie reviews. And the second sentence is, I hate this so much. And all we have to do is press the play button. And now the machine will tell you, the classifier will tell you, the first sentence has a positive sentiment and the second one has negative sentiment. And not only that, it'll even give you the confidence. So now it says, hey, 95% I'm confident that the first sentence is positive. Second one, it's much more confident. So 99% I am confident that the second sentence is negative. Now, interestingly, let's go ask it what the neutral, remember we had a neutral sentence earlier. So let's go back and ask the neutral sentence. The product is okay, I guess. Okay, so let's see. The product is okay, I guess. And we are going to ask for a sentiment. Now it says, okay, it thinks it's very high positive score. Let me see, kind of doable, likable, I guess. I'm just trying to confuse the machine and make it, let's see, its confidence is reducing when it says positive score. I'm going to say so. I don't even know it understands that. Aha, see, the score is reducing. So it's slowly going, it's saying, I think it's positive, but it's something close to neutral. while its score is for the negative is like it has memorized that hate means negative, right? So remember, that's the very first rule we told the machine. Here are some words. Most of the time, hate means negative, but then it gets confused with the medium or the neutral kind of situations. So the rest of the code here is kind of same thing. Like maybe here in classifier kind of masks a lot of the internal tasks, and it just gave you the one single output where the sentiment is positive or negative. Instead, we are going to break it step by step and say exactly what we saw in the class today, but we are going to go through each of the individual steps. And the first step is, here's a movie review, and I'm going to split it, or in other words, I'm going to tokenize it. And there's already like tokenization is at the root level, it's nothing but dot split command in Python. So the sentence, it splits it by the white space in between the word. But it gets more complex after a point because, if you have the word run and running, do you want run? Let's say people started asking questions like it's running. And if I tokenize it, do I want it to be run or NING? Or do I just want it to be called run so that I can use it for, run runnings? Maybe that was a bad example altogether. So let's say jump and jumping, right? So do I want to use it so that later I can reuse jumping instead of jumped, right? So those kind of tricks people have played, but fundamentally tokenization is nothing but dot split. You might have seen in Spacey has a tokenizer in itself. It's slightly more complicated than this, lot of apostrophes. Uh, let's see what it does for the apostrophes, right? So movies, currently, if you're just doing white space, it doesn't care. But that is not true meaning wise, because I want the movie having something which is the apostrophe S. So that is how we do tokenization. And even tokenization has its own models deep inside. So these are the names of the models. We have, like I said, dot split is the very basic one. So we can even like, this is a very well-known tokenizer like transformer itself, which has maybe more complex things um, than a white space splitting. So let's see. Here, it is more, the tokenizer in this case is more capable of separating I and have. And this, if you can print out, I think it should probably have a option for printing the words around it. So then now it gets into the language of more encoding. Like, let me give a unique ID for I. It's 101. Let me give a unique ID for bean, which is 1045. And now this is just engineering. Like, how can we exactly translate it and make sure we are talking about the same words, etc. Now, after that, what we load is something known as an auto model, which is the actual model which does like the task. What kind of task do you want to do? So if you look at it, you can see there are these models which are trained on English. This one is called Distilbert. Again, this is like at this point 5 years old, 10 years old. These were the original transformers that were used. And I'm teaching you the original so that eventually when I tell you ChatGPT has Distilbert deep inside, you'll be like, oh, I know. These were separate models that were created for, let's say, for sentiment analysis, right? So now all we do is we import the model. These are all pre-trained or already trained on the given task. And all we have to give it is inputs. Like the model, we create the object and we pass the inputs, which is the tokenized words, into the model, right? And we ask the model, give me an output, and it gives only these two numbers. And we don't know what these numbers mean. So we force the model to say that even if you have a 95% confidence, you need to tell me which class you're talking about. So initially the model just gave me two classes saying, the first review you gave me, I think it's more negative, more positive, things like that. And then we force it to like choose between two classes. And that's it. Essentially everything this thing did, the classifier did, we just broke it open and we have individual tasks inside it. And the same thing, I have been waiting for Hugging Face course my whole life. Now it gives you positive and negative, right? So those are like a basic introduction to a sentiment analysis model, which is like, at this point, it's considered prehistoric. Now the interesting part about pipeline is you can call anything you want, like text generation task. And I don't want to do like an old model like transformers. I want to use OpenAI's GPT. So it's as simple as replacing the pipeline. So you can go like Hugging Face and pipeline. Just go Hugging Face pipeline. You'll find the documentation for all this. Never mind. Hugging Face pipeline. And it'll give you a whole list of things you can do with all these individual. Here's text classification, here's GPT, and things like that. So in computer science at this point, it's all about read the manual. So now I want to say, hey, I want to do text generation. I'm going to say, hello, I'm a language model. You tell me what will you finish it with. Now, since we call the generator model text generation, it's good at text generation. And we are going to ask, let's see what it replies. It says, hello, I'm a language model for, E is a very big one, whatever that means. Hello, I'm a language model, he said, and leaned his left shoulder against the corner. So as you can see, the machine is just replacing the next word with the most frequently occurring word or words in the internet. Same thing, you can use it for my dog is cute. Tell me the sentiment for it. It'll give you a lot of these numbers, which you use the same trick, which is force it like before. Long story short, I introduce you to Hugging Face and pipeline, and those are the two fundamental things that you need to do any hands-on at a very fundamental level, right? So like if you really want to open up things and work on it, or maybe in the next class, we'll show you how to like call the actual GPT straight on, and which we are also doing here, right? If you don't want to do tokenization yourself, all you do is call the pipeline for it and give it generator, classifier, whatever. All right, we're almost at top of the hour. Quick time for 1 minute for questions.
So how
If-
do you, it is like a chat GPT, you can input both word and image. So how do I do it here?
Yeah, so in the command line, it's difficult to input images. So which is why we have, so you have to convert that into some sort of encoding. And the definition of encoding is, you have to bring it all down into zeros and ones. So yes, with just this thing alone, it's difficult to do it. But right now, if you want, I don't know if you were introduced to AI Word Day. So this is something we created recently for UofA students. In fact, you can drop us an email and we'll add you to one of these chatbots. We have one for OpenAI, we have one for DeepSeek and things like that. And we also have another course called Gen AI, which is actually happening in another 1 minute, or it should have started in 1 minute. And that's where we teach all this. Like today's class actually is multimodal. If you want to stay back for another next workshop, so that is where we have the answer to okay, to the question, Hoy, like if the very next class after this is teaching you how to upload images to AI Wording. Quickly, we'll answer what transformer actually is. Yeah, so encoder decoder is nothing but two transformers put next to each other. Since you can see my screen, if you put encoder decoder in the internet, Google search, that's it. See, these little boxes in here, each of those, that is a transformer network. The definition of encoding is, if you give it sentiment analysis, if you ask it to give encoding, it'll give you this. That's it. It just gives you numbers, and numbers are called encodings. But what do humans want? Humans want decoded, an English word, right? And I want to see the word positive or negative. So when you force it to give positive or negative, it's called decoding. So then what people realized is, I don't need the first part, or I can cut out the middle part, start reusing it. And that's how GPT was born. But that's a longer discussion, but that's it. Like deep inside, it's just all transformers. It's all chained up layers and layers of transformers. All right, I'm already eating into 2 minutes of the next class. Thank you all. Hope you learned something new. All the slides are up in the same link we posted.